All right, so what we're going to look at today are some linear models and scatter plots. We'll be using our calculators a bit on this. And exactly what we will be doing is we're going to look at constructing a scatter plot and interpret the correlation of the plots on the graph. And then we're going to use these in a graphing utility to find linear models for data so that we can predict outcome. And let me turn off the light over here. So, can you get that left one?
This one?
Yes, thank you.
You're welcome.
All right, so I don't think we'll have too much trouble with this. This isn't too bad. Scatter plots and correlation. Many real-life situations involve finding relationships between two variables, such as the year and the number of employees in the cell phone industry. In a typical situation, data are collected and written as a set of ordered pairs. The graph of such a set is called a scatter plot. So I think y'all have all seen scatter plots before. So here's some data. This data shows the number E in thousands. It's always important to notice that too, that if what a number actually represents. So in thousands of employees in the cellular telecommunications industry in the United States from the years 2002 through 2007, construct a scatter plot of the data. So basically what we're doing for a scatter plot, right, is we're just creating ordered pairs out of these numbers. We are then plotting them on a graph. Now, a lot of times you'll have to change the units on your graph or whatever to make sure the data fits on there. So if you'll notice here in the year 2002, there was 192,000. In 2003, 206,000, and so on down through 2007, where there's 267,000 employees. All right, so this is a set of data. So what we're going to do is we're going to use this data, and we're going to basically use this data to create an equation of a line so that we can predict later values of this information. And let's see what they did with it. All right, so we begin by representing the data with a set of ordered pairs. Let T represent the year. And notice this is done a lot too, so that we can fit it on our graph better. We're letting T equal 2 correspond to the year 2002. So when T is 3, that's 2003, and so on and so forth. So the 4 or the 6 ordered pairs they come up with are 2, 192, 3, 206, so on. You can see that. And then notice they plotted each point in a coordinate plane. Notice up the left-hand side, they went up by units of 40, and then on the bottom, they went up by units of 1. Notice, too, that the bottom, if I zoom in on this graph, down here, they've got this little broken line or little Z-looking thing. That's just saying that we've sort of picked up in the middle of something. It's not all the way over to 0, 0. The corner would be 0, 0, although it was such a low number they could have, but they've skipped one. But they only needed 2 through 7 because we're only looking at 2002 through 2007. All right. Now, what we're looking for is when we make a scatter plot is, let's see if this is what it talks about. It talks about correlation. All right. From that figure we just looked at, we can say that a mathematical equation that approximates the relationship between T and E is a mathematical model. When developing a mathematical model to describe a set of data, you strive for 2 often conflicting goals: accuracy and simplicity. For the data above, a linear model of the form E equals AT plus B, where A and B are constants, appear to be best. It is simple and relatively accurate. So a lot of times what we'll be looking for is a linear model, which if we look back up at the scatter plot, it generally is forming a line. Okay, and that's kind of what we're looking for today. We're looking for scatter plots that will generally or line up and form a line so that we can come up with the line. And notice this right here, this E equals AT plus B is very similar to what we've always known as slope-intercept form. Y equals mx plus b. So the b is essentially where that line crosses the x or the y-axis, and the a or the m is the slope of the line. So if I wanted to go and try to start looking at an equation of this line, if I were to sort of draw a line through it, which is sort of what we'll be doing, I can see that the y-intercept would be, in between 140 and 200, or is that 160? Between 160 and 200. So it's about 175, 180 maybe. The slope, I could use 2 points on there, but we'll talk more about that in a minute. But that's sort of the idea of what we're doing. All right, consider a collection of ordered pairs in the form xy. If y tends to increase as x increases, then the collection is said to have a positive correlation. Positive correlation means that it sort of lines up and it's an uphill line. If y tends to decrease as x increases, then the collection is said to have a negative correlation. So if it sort of lines up as a line going downhill, that is what we call a negative correlation. The correlation means that it's sort of forming a line. All right, so here are three examples. We could see the first one, the points are very much lined up around, like if I drew a line, which is called a line of best fit through them, those points are all pretty much around that. We could say this has a good, strong, positive correlation. Positive because it's going uphill. Same thing here is we can see that this lines up pretty well right there. This would be a strong negative correlation because it is going downhill as we go from left to right. It would have a negative slope. First one's a positive slope, the second one's a negative slope. And then the third one, as you can see, there's no way I could choose to draw a line that would closely resemble that. That's no correlation at all. So obviously, what we're looking for with this data is we're looking for strong correlations. We're going to be looking for a strong positive or a strong negative correlation. If there is no correlation at all, then it's obviously going to be hard to make a prediction or to come up with some sort of equation. You won't be able to. So, all right. So let's look at another example. And in this example, 22 students in a class were asked to record the number of hours they spent studying for a test on Monday and the number of hours they spent watching television. The results are shown below. The first coordinate is the number of hours, and the second coordinate is the score obtained on the test. So the first number is the number of hours studied. The second number is their score on the test. And so we're going to see if there is a correlation between the number of hours studied to the score on the test. All right. So we can glance through. The person that studied 0 made a 40 on the test. The person that studied 1 hour made a 41. Look at the end. The person that studied the most, 10 hours, made a 98. But notice it's not always holding true. So this person studied 9 hours and made a 72. This one studied 9 hours, made a 95. So it's not going to be an exact correlation, but it looks like as the more hours you study, the higher your test score is. So we're going to look and see if this does form a good correlation. All right, this is also the number of TV hours. So this is a second one that's comparing how many hours they spent watching TV to their score. All right, does it make a difference? Is it correlated? The person that took 0 hours on TV scored a 98. The person that was 20 hours of TV made a 40. All right. Construct a scatter plot for each of the set of data and determine whether points are positively correlated or negatively correlated or have no discernible correlation. What can you conclude? So we're not going to actually draw this out. I feel confident that everybody can plot points on a graph. All right. So the first one there is the test score, comparing the test score and the number of hours studied. So as you go to the right, more hours of study, notice the numbers are typically going up. And I'm going to have to, I don't know if I still have this line. I've got to do this so I can find this. So as you can see, there is a fairly, if I wanted to draw what we call a line of best fit, there is a line in there that lines up. It is very easy to see that that is a positive correlation. And then as you see here, whoops, I have to actually draw that again. The more TV hours of TV, the less, generally speaking, the less you scored on the test. So there is a strong or a good negative correlation based on that. So that's what they did. They plotted the points. So you just have to be able to find a graph. And actually, we're going to show you on the calculator in a minute how you can enter the points. I'm sure you've done it before. Most of you have done it before. And look at it. But there's a strong correlation. There's a negative correlation. So there is a correlation they're seeing between study hours and score, and then hours watching TV and the score. And that's what we just talked about. All right, fitting a line to data. And this is sort of the crux of what we're talking about today, and the most important part of what we're being able to talk about is being able to come up with a line. All right, finding a linear model to represent the relationship described by a scatter plot is calling fitting a line to data, or the line of best fit is sort of how I've described it. All right, so if we go back to this first one where the years worked and the number of employees for this cell phone company, we want to find, so when they say find a linear model, that means write an equation for a line. Okay, that's what it is. A model is an equation for a line. All right. So here's what the way they do that. Now, doing this by hand, and we're also going to look at how we're doing this on the computer, on the calculator, I mean. So here's that data again. All right. There is a line. That's what they've done, is drawn a line of best fit through that data. All right. And we're still letting T equals 2 as corresponds to the year 2002. After plotting the data on the table, draw the line that you think best represents the data. 2 points that lie on this line are, so what they've done is they've taken 2 of the points that are actually on the line of best fit. So if you noticed, let me zoom into this. When they drew their line of best fit, what they're saying is this point and this point are the 2 points that are on that particular line the best. All right. And everybody's line of best fit could look just a little bit different, but when you draw it, you sort of want to make it in the middle of the points. You want the same amount of points above and below, if possible, or relatively similar. Okay. But everybody should be able to see that this is a good line of best fit. And so what we do is we take, since those 2 points are on that line, here were the ordered pairs associated with that point. All right. And so what we're going to do is we're going to create an equation of that line. Let's see if they go through and show how they did it. All right, so yeah, that's what they do. So we'll go ahead and do this using point slope form. So if we remember, point slope form of equation is y minus y sub 1 equals m times x minus x sub 1. So the first thing we want to do is find the slope. Remember, slope is y minus y over x minus x. So this is 254 minus 206 over 6 minus 3. And it looks like that's going to be 16. Let me type it in my calculator real quick. 254 minus 206 over 6 minus 3. It is 16. So the slope is 16. And then we can use either point, either one of those points, to substitute into our point slope formula. So I'm going to say y minus 206 equals 16 times x minus 3. And then we just want to solve it for y. So I distribute the 16. So that's going to be 16x minus 48. And then I add 206. And that's where we get y equals 11x, or I'm sorry, 16x. That's a 16. 16x plus, what am I getting here? 206. Make sure I get that. 16 times 3 is 48. Negative 48 plus 206 is 158. Yep, plus 158. All right, now, so what this tells us is this is the equation of that line. So this is the model for this situation. And so what we can do is with this, the x, I used x and y. The x-axis is the year, the y-axis is the number of employees in thousands. So if I wanted to know, based on this, in the year 2010 or the year 2020, how many employees they have, all I would have to do, if I wanted to know how many employees for the year 2020, well, we're using 234, that's 2002, 2003. So what I would be using is 20. What I would do is I would simply plug 20 in for X and then work that out. And that will then tell me how many thousands of people are working at this telephone company. All right. So that's the whole idea of what we're doing is we're looking at a set of data, looking at a line of best fit, and then we're coming up for the equation for that line. Okay. And the next step will be to look at these calculators and show you how to do that. I'm going to write down this. I'm going to take a picture of this real quick so I can pull it up and use it in just a minute if I need to. All right, let's see if they say anything on this slideshow about, there's a linear model. It says once you found the model or the equation, you can measure how well the model fits the data by comparing the actual values with the values given by the model. So you could plug in the different X values and see what you get and then compare it to the model. You'll notice that it's not exact. This is not an exact science, all right? But it does give us pretty good a pretty good estimation. Now, what they're talking about here is to tell how, I think this is going to be talking about how good of a model it is. So what they've done is they took the formula. This is from the formula that they created when they substituted in 2 through 7. And the model is the actual, I'm sorry, the first row right here is the actual data, and this is from substituting into that equation. The sum of the squares of the differences between the actual values and the model values is called the sum of the squared differences. And let's show you. Well, I don't think they're really going to get into that. The model that has the least sum is called the least squares regression line for the data. For the model in example 3, the sum of the squared differences is 54. The least squared regression line for the data is 15t plus 162. It is sum square difference is 37. Another way to find a linear model to represent the relationship described by the scatter plot is then data points into a graphing utility. So what they're saying is, and we're not really going to get into this, so I'm not going to spend a lot of time on it. The sum of the squares of the differences, what they would do is find the difference between these two. The difference is 2, the difference is 0, the difference is 4, the difference is 5, 0, and 3. And then they would square all these. 2 squared is 4. And I would add them. 0 plus 16 plus 25 plus 0 plus 9. And what they're saying is that sum equals 54. And what they've done and what your calculator will do is they found that if they use 162 here, that the sum of those square differences is 37, which the lower that number is means the better fit the linear model is. Okay, but I'm not really concerned about that right now because we're going to use a calculator, and I just want you to be able to find the equation. So let's go on. And they're going back to example 4. So, yeah, we're using the same stuff. So here's what we're going to do. Well, actually, this is a different one. This says the data on the table shown is the estimate number V in thousands of alternatively fueled vehicles in use in the United States from 2001 through 2007. So in 2001, there was 425,000 hybrid vehicles. By 2007, it was up to 696,000 hybrid vehicles or electric vehicles or whatever. So that's our data. All right. And I need to take a picture of that so I have the information. All right. So here's what we do on our calculator when we have that data. All right. So here's the important part. All right. I need to clear out this. And it's been a while since I've done this, so hopefully I can remember all the steps. Let's see. Stats. Is it stats? Yep. I think it's going to, you hit the stats button on this calculator, and then it's the very first one to edit there. And I believe this is where we're going to enter the information. All right. And L1 is that's going to be the X coordinates of each point, and L2 is going to have its corresponding Y coordinates. And let me pull that photo back up so I can see the points. So I'm going to say 1. Now I have to double check this to make sure it's right. Like I said, it's been a while since I've done this. 3, 4, 5, 6, 7. And then I'm going to go over to L2, and I'm going to put in the Y coordinates or the secondary points there. So 1, 425, 2, 471, 534, 565, 592, 635, and 696. All right, so then I'm going to double check to make sure I've got those in there right. So I went to stat and edit, and I've been able to enter that information in. Now let's go back to the PowerPoint here and see. I don't believe they're going to actually explain how to do it, so I think I've got to go through. All right. All right, so I've got the points in, and then I'm going to quit out of that, and then I'm going to hit stat, and then I believe I go over to calc. Yep. And I believe it is the line reg right here. Notice right here, the fourth one down, it's got the AX plus B. All right, it's asking us to put it in AX plus B form. So if I pick 4, and there, to make sure you've got the right list, I used the X list was L1, the Y list was L2. So if you'd use others of those lines, you would have to change which lines you're using. So make sure you got there, and I don't believe the other one's mentioned. So I'm just going to enter through everything and hit calculate. And if you notice right there, here's where we get our answer. It says y equals ax plus b. Then it tells us the value of a, which the value of a, we're going to take it to the 10th, is 42.8. And the value of b is 388.4. Well, the a value is basically our slope. The b value is basically our y-intercept. So to write the equation based on this is exactly where they got this right here. The a value we said was 42.8, and the b value was 388.4. They went ahead and rounded that to 388. And so the a was a slope, the b was a y-intercept, so there we can write our equation. So as you can see, it is very simple to write that equation using our calculator. So just review on our calculator real quick. What did we do? All right, let me quit. We hit stat, and then edit will allow us to enter our information. Okay, right? The x coordinate in L1, the y coordinate's in L2. And then I quit out of that and I hit stat, and then I arrow over to calc, and it is the line reg, number 4 there. Is what we're looking for when we are making a line, when it's forming a linear regression. It means linear regression, basically is what that means. Make sure I've got the X list and the Y variables correct, hit calculate, and there you go. It tells you that. It tells you the slope and the y-intercept you're going to use to create this equation. Okay? So pretty simple stuff there. And then here they're listing, they're going through and putting in, they're using the actual data and the model, or using the equation to get here and to see and compare exactly how good this is. And this is where we get, when you use the regression feature on a graphing calculator or computer program to find a linear model for data, you will notice that the program may also output an R value. For instance, the R value from example 4 was R, and ours did not put out an R view. So let me see if I can figure out what's going on with that. Stats. I may have to go down. I can't remember. I may have to look that up. Well, my fingers are too big to keep hitting the buttons here. Let me see. Well, I'll have to get back on that part. For some reason, this calculator is not set up correctly. I may have to do. All right, let's see if that maybe does it. There it is. Okay, so what we have to do is on your mode, you have to go down and put stat diagnostics to on. And then what you'll notice is the R value. Let me pull it back up. Is this what they're talking about? That's 4. All right, so the R value and the R squared value, so it gives you what the A is, the B. This is basically going to tell you how good of an estimate this is. And now let me go back to that other, and here's what they're talking about that. For instance, the R value from example 4 was 0.994. This R value is the correlation coefficient. So that R value is what's called the correlation coefficient. It tells you how well this information is correlated and gives a measure of how well the model fits the data. The correlation coefficient R varies between -1 and 1. Basically, the closer the absolute value of R is to 1, the better the points can be described by a line. So the closer, if we go back to that calculator and we're looking at the R value, the closer this R value is to plus or minus 1, the better that this model or this prediction can be. So if that were like 0.1, that means that the points aren't correlated at all. 0.994 essentially is very close to 1. So that means it has a very good correlation. That is its correlation coefficient, 0.994. Okay, so whenever you do this, you do need to take note of that R. And once again, I had to go to mode and down to stat diagnostics and put it on to get it to show this. All right, this tells me this is a good predictor of what's going on, that if I did the scatter plot, it would have a very good line of best fit. All right. And let's see. All right, so once again, there's 3 examples. The first one is just showing you the correlation. Notice those lines are all, that's pretty good line of best fit there, and its correlation line was 0.972. Well, the one we had was 0.994, so it would the points were even more lined up than those, and those are lined up pretty well. If you notice the next one, and you'll also notice that it's negative when it's going downhill and it's positive when it's going uphill. These points aren't lined up as well, but they still are in a decent line. I could get a decent projection out of that. It's negative 0.856. And then notice when it is 0.19, they're scattered all over the place. I'm not really getting any kind of good prediction from that at all. And I believe that's it. All right, so just to rehash on the calculator. All right, we need to make sure for this that I go to mode. The stat diagnostics is on. And then I hit stat and edit to enter my X and Y coordinates. And then I hit stat and go over to calc. And I'm going down to the 4th one, line reg. and hit enter. I just enter all the way through, and it gives me my slope and y-intercept of the line of best fit. And then I look at that, the R value. As it approaches 1, it's a better and better prediction. It lines up better and better. The farther it gets or closer it gets to 0, then the more scattered the points are. And that's it. So now I'll go ahead and open up the next assignment, and I'll go open up the test review. That way, as you get done with these assignments, you can go ahead and start making these test reviews. And I'll make this stuff due next Friday.